All right, welcome back. We're starting a new chapter, chapter 2 of the book, and we are going to be learning about randomness, okay? Randomness. Okay. Randomness, okay? Randomness is very important in cryptography and is a big part of every cryptographic scheme. It's important in key generation, for example, but it's also important on the attacker side. Attacks use randomness. Attacks to encryption also use randomness. So that's why we're going to learn about randomness. And guys, no cryptography would work. Cryptography would not be a thing without randomness. Why? Because if every process is determinable and and can be determined and predictable, then how are we going to be able to obfuscate some data? Everybody will be able to figure out the process that got the data to us, so through which we obfuscate the data. So having randomness creates this non-predictability, and so you don't know how to decipher things, for example. And that's why, again, it's important to learn randomness. So let's talk a little bit about random, what it means, We'll look at random versus non-random. Okay? Perfect. So let's take a random number in base 2. So I'll take a pair, okay? Okay, and then I'm gonna take this one. Okay, they're both 8-bit numbers in base 2. And one thing that I want to say and make sure that everybody knows is that it's not that these numbers are random per se. But it's not that randoms are number. Random numbers means that the algorithm that generated those randoms is random, okay? So it's more of a, what can I say? I'll get it right here, randomly generated, exactly. So, to these ones, the thing that I want to make sure everybody knows is that for humans, which ones, actually I'll start with this question, which one of these two numbers to you looks random? This one, right? This one looks random. Because we as humans, so this one looks random and this one does not look random at all. But from the pure theoretical perspective, these are can be both random numbers, right? This can be generated by a random algorithm, but this also is a valid number that can be generated from an algorithm. And so we humans, we're amazing. We have this amazing, we're amazing animals, but unfortunately we have a high bias towards looking at patterns, okay? So if we look at this string, there's not really something that we can infer, but in here we can see that it's all zeros. And while here there's a little bit of ones and zeros, and we can see rearranging and everything, this one does not look random. So we have as humans, we have a tendency to look at patterns, to look at things like this and think that they're not random. And so it's very important to know this, because we, again, because humans are attracted to patterns and things like this, always we have a bias to think, to mistake, for example, if a random number generator gives us this, we might not believe that is random. And if a non-random number generator gives us this, we can be like a non-random. To us humans, it might still look random, right? And so we have this bias and tendency to judge random and non-random. So just keep this in mind at all times. All right, let's talk a bit. I'm gonna delete this to make some space. Let's talk about the probability. So actually, yeah, probability. Why are we talking about probability of randomness? Okay, we're talking about probability because since we're talking about generating random numbers, the act of generating random numbers is a process, right? And a process has outcomes. And so outcomes of a process can be all laid out and be considered as a probability distribution. So we can look at the probability distribution, right, of a random number generator and assess how random that process really is, right? And again, what do we mean by probability? By probability, we mean the likelihood that a certain event happens, right? And it is a number from 0 to 1, okay? I'm just reviewing a little bit. And 0 means impossible, event impossible to happen, and 1, event absolutely certain to happen, okay? So let's go on. The way that you count a probability of a process that throws output, that gives outputs, is with this formula. Let me just check so I don't write it wrong. So let's say we have n events, right? We'll call the probability distribution of n events out of a process as the probability of the first event plus the probability of the second event plus the probability of the third, the fourth, and fifth n events. Actually, I should write the n in lowercase. Okay? And guys, the sum of all the probabilities always equals to 1. Okay? Perfect. So let's make an example of a coin, right? We have a coin toss. Do I have a coin in my pocket? No, I don't have a coin in my pocket. Who uses coins anymore? It's all digital now. Let's do a coin toss. So I have a coin toss. I can either have two outcomes, either heads or tails, right? Let's not consider the coin. Let's pretend that the coin cannot land on the side. It's always going to land either on heads or tails. And so we can say that a coin toss has, what's the probability of heads? So the coin toss has two outcomes, right? One is heads and one is tails. The probability of getting heads is a half, right? It's not impossible, it's not certain, it's a half. And the probability to get tails is a half. Together they make 1, okay? So what we call something like this, and this can be true also for dice, right? Dices, you have a chance, they have 6 sides, so you have a chance out of 6 to roll a number on a fair dice. And so coin, and then 1/6 plus 1/6, for each side of the dice will give the probability of the dice, okay? So this is called the uniform distribution, okay? Why? Because every probability, every event has equal chance to happen, okay? has equal chance to happen. So, for example, if we have a I'm gonna call this actually fair coin, okay? A coin that is not tricked, that it will always be half. So this is a uniform distribution, and basically if you want to make another example, we want to pick a key of 128 bits, right? So we're going to have 128 slots like this, right? And we're going to have either 0 or we're going to have 1 for each slot, right? And so the algorithm will pick, etc., for all 128 slots. And so we have a 2 for a 128 key or string. We'll call it a key because that's what I call it. We're making a cryptography example, so a key of 128 bits, where each bit has been picked with a uniform distribution, so there's equal likeliness to each bit. Then we have a what's it called? We have basically 200 and 1 to the 128. Sorry, 2 to the 128, 128 possible keys. Right? This is a huge number, right? And so what is the probability of me guessing the right key if this key is generated with a uniform distribution? Okay? The probability of picking the correct key and guessing it right is 1 over is to the 128, okay? I'm not referring directly to any formula, I'm just quantifying, right? If we have a uniform distribution, which means every element of the key is picked with a with a 1/2 possibility, then we're gonna have 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 120 times. So this is why uniform distribution is important. Now we also have a non-uniform distribution. So a non-uniform distribution is, for example, when we have a tricked coin, right? So in a tricked coin, a coin that has been tampered with, we're gonna have, for example, let's say 3/4 of a chance to get heads and only 1/4 of a chance to get tails. Always the probability needs to sum to 1, right? This is a, how can I call it? Tricked coin. This is all right. Non-uniform distribution. All right. So why? So in cryptography, you guess right. You want your key picked with a uniform distribution. You want uniform distribution in cryptography. Why? Because if we don't have a uniform distribution, then we know that getting a certain outcome from the process is more likely, and therefore, put yourself as an attacker, you're going to know that if you start guessing the key, for example, with certain numbers, because you know that I mean, I'm jumping a bit of example. Let's stick in the coin. If I want to predict the coin toss, here it's much harder to predict the coin toss, the result, compared to here. Here I can pretty much say, okay, we're getting heads, and I'm pretty much right most of the times, okay? And so we don't want that to happen in cryptography. On a key generation algorithm, we want every single bit to be chosen randomly with a uniform distribution. Because if that's not the case, attackers will know that they can start testing a few keys with certain values before others, and so their chances of attack increases, right? So pretty simple until now. Let's continue with talking about something very important related to randomness, which is entropy. Entropy, the concept of entropy always has fascinated me. Always. And I wrote down a definition. The entropy is uncertainty and disorder in a system. Okay, uncertainty, disorder. The book gives also a very interesting alternative definition. It says that it's also the amount of surprise that you find in the result of a randomized process, okay? Kanatize gives a definition of entropy tied to what we were talking about before. So if the outcome of a process is very surprising, then the entropy is high, right? The higher the entropy, the less certain is, the less you're certain of the result that you're gonna get, right? So how do we calculate it, right? Let's do some math. How do we calculate entropy? So we use this kind of formula. We take all the probabilities of a process, and we take the negative of each probability. So let's say this is a probability of the first outcome, and we multiply it with the logarithm, with the logarithm in base 2 of 1 over the probability. Okay? Sorry guys, P1. Voila. Okay? Minus the second event, and you guessed it right. It's going to be the same for any events n log of n. Okay? So, should we calculate the also, just to give you a little bit of a background, how do we calculate the log in base 2? Let's open a little off topic here. If we have a log in base 2 of 1/2, then it's going to be -1. If we have a log of 1/4, remember that 1/4 is 2 to the second, so it's going to be -2. That's how you calculate the log in base 2. So we can generalize it that log of 1 over n is equal to -n, right? Sorry, what am I doing? 1 log of 1, that's super wrong. 1 of 2 to the n is going to be equal to -n, because it's the logarithm in base 2. It's the exponent that we put to 2 so that we get this number. Alright, so now that we've looked a little bit how to calculate this, and we gave a definition a mathematical definition of entropy, let's make the example of the 128 bit key, right? That was before. Actually, let's make it with the coin toss. Why not? With the coin toss, it's gonna be 1/2 times log of 1/2 minus 1/2. Actually, I'm gonna do it later, the coin toss example, because Yeah, I have it later because I'm gonna compare it with the coin toss of a fair one and non-fair one. I'm skipping a bit ahead. Let's do the example with the 128 key bits, right? So with the 128 key bits, we're going to have an entropy of, let's see how I wrote it down here. So I'm gonna look at directly on the book. There we go. All right, so with the random 128 bit keys produced using a uniform distribution, we're gonna have the following entropy. So we're gonna have 2 to the 128. I don't know why the book is not following, but let me figure it out. 2 to 128 times minus 2 to minus 128. So actually I'm gonna write it like the book does. Minus 128, which means is 1 over 128, times the log of 2 minus 128, which is equal to the log minus log. Okay, so you cancel out and you get minus log 2 to the 128, which gives the 128. Interesting, right? So the entropy of a key, of a 128-bit key generated using a uniform distribution is 128 bits. Interesting, huh? What does that mean? It means that the entropy of a uniformly distributed n-bit string is n, right? 128 is n. So you cannot have more entropy than n because those are all the bits that you can combine together in that string. So the fact that the entropy is high, it means that our uncertainty is max. Okay, max uncertainty. So no outcome is more likely to happen than another. That's what the definition of a high entropy is in this case. So let's make this example with a coin toss, and I'm actually going to use this formula, follow this formula properly. All right, so the coin toss, we said it's 2 probabilities, heads or tails, and each one a fair coin first. Okay, a fair coin is going to have 2 probabilities, 1/2 each. So how do we calculate the entropy of this? We're going to do minus 1/2 times log base 2 of 1/2 minus 1 over 2, so this is the heads, and this is the second probability of tails, log of 1/2. Okay, simply following this formula. So what does this give us? This will give us the minus, will give us 1/2, right, here, because this is equal to minus 1, so minus 1 times minus 1/2 is 1/2, and then this is going to be also minus 1 multiplied by is going to be plus 1/2, and there you go. The entropy of a fair coin toss is 1. Okay, now let's calculate the entropy of a non-fair coin toss. Tricked coin, but I don't like to call it tricked. Like tampered coin, or like, how do you call when you mess around with the casino things, or you more like when you're like tricked? Whatever, I don't like tricked. Tricked coin, right? The coin that has been messed around a little bit, so one side is more likely than the other. In the trick coin, let's say that the odds of getting heads are 3/4, right? So P1 is going to be 3/4 log of 3/4 minus 1/4, right? Because now we have this probability of getting heads and this probability of getting tails. Perfect. Now we're gonna have, I just wrote down the result already, minus 3/4. So I mean, I made the calculation here on paper, minus 3/4. The point is that it's equal to 0.81. Okay, so now let's think about it. Tricked coin, fair coin. The fair coin has a higher entropy, higher uncertainty of what's going to happen. But this is the value of entropy we're calculating. The one that is tricked has less entropy. Why? Because we can guess with more certainty that one outcome, which in this case is heads, is more likely to happen than tails. Okay? And so for a less uniformly, so we know that the tricked coin is a non-uniform distribution, while the fair coin is a uniform distribution. We can conclude that uniform distributions have higher entropy than a non-uniform distribution. Let's prove it even further, or at least let's illustrate, give example even further. If heads now was going to be 110 instead of actually no, if I think the example well, let's say that this outcome would have been 110 instead of 1/4, so this would have been, you know, appropriately the other obviously remember P1 plus P2, they always need to be equal to 1. They always need to 1. Remember P1, P2, they always need to be equal to 1. So if in this case the coin toss is 1/10, then this one would be the, I don't want to do the calculation, but let's say we substitute, so we reduce even more the chances of getting tails and we increase even more the chances of getting heads. What's going to happen to the entropy? The value of entropy, I wrote it down, calculated before, I mean the book gives this example, is 0.469. Right? What if it's 1/100? Then in this case it's going to be 0.081. Yeah, it's going to be 0.1. So the more we mess around with the coin and we trick it to get always heads or always tails, the lower the entropy value falls. Okay? Here, very low entropy, because I only have a chance out of 100 to get a tails. So I know pretty much that there's not too much uncertainty, there's not too much disorder. I'm always gonna have an outcome more particular, more prone to happen than other ones. And this concludes the part on randomness, the introduction to randomness and entropy. And in the next video we're going to look at the random number generators and pseudo-random number generators, the actual processes that generate the numbers. So for this one, just keep in mind we went through probability, the distributions, uniform distribution, and then this is a good introduction, very interesting. I enjoyed learning about this, and I'm excited for continuing. So thank you for watching. Thank you. If you got to this point, you are a champ, and I hope you're understanding cryptography fully, even if the videos are long. But this, I guess this is it's part of learning well, taking the time to learn. So guys, thank you. I'll see you next time. Bye bye. Link and subscribe, obviously. That's always hi. Bye bye.